technology for production and use of inorganic materials such as porcelain, ceramic and glass. Manufacturing and utilization of inorganic materials, ceramics, pottery, and glass. Inorganic materials such as ceramics, pottery, and glass have been used for centuries as essential components in a wide range of industries. The production and use of these materials have evolved over time, with advances in technology and materials science leading to new and innovative applications. Ceramics are a type of inorganic material that is typically made from clay, feldspar, and other minerals. They are known for their high temperature resistance, strength, and durability, making them ideal for use in a variety of applications. One of the most common applications of ceramics is in the production of pottery, which has been used for thousands of years for utilitarian and decorative purposes. Pottery can be made using a variety of techniques, including hand building, throwing, and molding. In addition to pottery, ceramics are also used in a variety of industries, including aerospace, electronics, and energy. For example, ceramics are used in the production of jet engine components, electronic substrates, and fuel cells. The production of ceramics involves several key processes, including shaping, drying, firing, and glazing. Advances in technology have led to new and innovative techniques for the production of ceramics, such as 3D printing, which allows for the creation of complex and intricate shapes. Pottery is a type of ceramic that is primarily used for decorative and utilitarian purposes. It has been used for thousands of years, with examples of pottery dating back to ancient civilizations such as the Egyptians, Greeks, and Chinese. The production of pottery involves several key processes, including shaping, drying, firing, and glazing. Pottery can be made using a variety of techniques, including hand building, throwing, and molding. In addition to its decorative and utilitarian uses, pottery is also used in the production of art and sculpture. Many contemporary artists use pottery as a medium for their work, creating intricate and beautiful pieces that push the boundaries of traditional pottery techniques and styles. Glass is another type of inorganic material that has been used for centuries in a variety of applications. It is made from a mixture of silica sand, soda ash, and limestone, which are melted together at high temperatures to form a molten glass. One of the most common applications of glass is in the production of windows and mirrors. Glass is also used in the production of consumer products such as bottles, jars, and lenses. The production of glass involves several key processes, including melting, forming, and annealing. Advances in technology have led to new and innovative techniques for the production of glass, such as float glass, which allows for the creation of large, flat sheets of glass for use in windows and other applications. In addition to its traditional uses, glass is also used in the production of art and sculpture. Many contemporary artists use glass as a medium for their work, creating unique and beautiful pieces that push the boundaries of traditional glass-blowing techniques and styles. Conclusion. The production and use of inorganic materials such as ceramics, pottery, and glass have a long and rich history, with applications in a wide range of industries and fields. Advances in technology and materials science have led to new and innovative techniques for the production of these materials, allowing for the creation of complex and intricate shapes and designs. While these materials have many benefits, they also have some challenges and considerations to be taken into account. For example, the production of ceramics and glass can be resource-intensive and potentially harmful to the environment. It is important to ensure that the production and use of these materials are guided by ethical and sustainable principles, with a focus on promoting access and equity. The production and use of inorganic materials such as ceramics, pottery, and glass also have significant cultural and historical importance. These materials have been used for centuries by different cultures around the world to create unique and beautiful works of art, architecture, and design. In particular, pottery and ceramics have a long tradition in many cultures, with each region having its own distinctive styles and techniques. In Japan, for example, pottery is an important aspect of traditional culture, with the famous Japanese tea ceremony using unique ceramic teaware. Similarly, glass has played an important role in the history of many cultures, with the ancient Romans being particularly renowned for their glassmaking skills. Today, glass continues to be used in the production of decorative objects and art. With contemporary glass artists pushing the boundaries of traditional glassblowing techniques and creating innovative and striking pieces. In addition to their cultural and historical significance, inorganic materials such as ceramics, pottery, and glass also have important practical applications in the modern world. For example, ceramics are used in the production of advanced materials such as superconductors and catalysts for chemical reactions. While glass is used in the production of optical fibers for telecommunications and medical devices such as lenses and syringes. Furthermore, recent developments in materials science and engineering have led to the creation of new and innovative types of inorganic materials with unique properties and applications. For example, researchers have developed new types of ceramic materials that are lightweight and strong, making them ideal for use in aerospace and automotive applications. Along with the traditional uses of inorganic materials such as ceramics, pottery, and glass, there are also emerging applications that show great promise for the future. One such application is the use of ceramics and glass in the development of new types of batteries and energy storage systems. For example, researchers are exploring the use of ceramic materials in solid-state batteries, which have the potential to provide higher energy density, longer lifespan, and improved safety compared to traditional lithium-ion batteries. Similarly, glass has been used in the development of sodium-ion batteries, which have the potential to provide a lower cost and more environmentally friendly alternative to lithium-ion batteries. These batteries use glass as a solid electrolyte, which helps to improve their safety and performance. In addition, inorganic materials are also being used in the development of new technologies for water treatment and purification. For example, ceramic membranes are being used to filter and purify water in a variety of applications, including desalination and wastewater treatment. Furthermore, inorganic materials are also being used in the development of new technologies for air purification and pollution control. For example, ceramic filters are being used to remove pollutants such as particulate matter and nitrogen oxides from the exhaust gases of diesel engines. Another emerging application of inorganic materials is their use in the development of advanced sensors and electronics. In particular, ceramic and glass materials are being used to create sensors that can detect a wide range of physical and chemical properties, such as temperature, pressure, and gas concentration. For example, ceramic sensors are being used in automotive applications to monitor engine performance and emissions, while glass sensors are being used in medical applications to monitor blood glucose levels and other vital signs. In addition, inorganic materials are being used in the development of advanced electronics, such as thin film transistors and flexible displays.
Neutralization reactions and properties of inorganic acids such as sulfuric acid, nitric acid, and hydrochloric acid. Acid-base reactions are an essential part of chemistry, and the properties of inorganic acids such as sulfuric acid, nitric acid, and hydrochloric acid are of particular interest. These acids are widely used in industry and research, and their properties have important implications for a range of applications. Sulfuric acid, also known as oil of vitriol, is a strong and highly corrosive acid with the chemical formula H2SO4. It is commonly used in the production of fertilizers, detergents, and other chemicals, as well as in the processing of metals such as copper and zinc. Sulfuric acid is also used in the purification of petroleum and in the production of batteries. One of the key properties of sulfuric acid is its strong acidity, which makes it a powerful oxidizing agent. It can react with a wide range of substances, including metals, bases, and organic compounds, and can cause severe burns if it comes into contact with skin or eyes. Sulfuric acid is also highly hygroscopic, meaning it readily absorbs moisture from the air and can generate significant heat if mixed with water. Nitric acid, with the chemical formula NO3, is another strong and highly reactive acid. It is commonly used in the production of fertilizers, dyes, and other chemicals, as well as in the manufacturing of explosives such as nitroglycerin. Nitric acid is also used in the production of semiconductors and in the etching of metals. Like sulfuric acid, nitric acid is a strong oxidizing agent and can react with a range of substances. It is particularly reactive with metals, and can dissolve many common metals such as copper and silver. Nitric acid is also a corrosive and hazardous substance, and can cause severe burns if not handled properly. Hydrochloric acid, with the chemical formula HCl, is a strong and highly acidic solution commonly used in industry and research. It is used in the production of a wide range of chemicals, including pharmaceuticals, dyes, and fertilizers, as well as in the processing of metals such as steel and aluminum. Hydrochloric acid is also used in the cleaning and maintenance of swimming pools and in the pickling of metals. Like sulfuric acid and nitric acid, hydrochloric acid is highly reactive and can cause severe burns if not handled properly. One of the key properties of hydrochloric acid is its ability to dissolve many common metals, including iron, zinc, and nickel. It is also a strong acid, with a pH of less than 1, and can react with a range of substances to form salts and other compounds. In addition to their industrial and environmental applications, inorganic acids also have important biological and physiological implications. For example, hydrochloric acid is a key component of gastric acid, which is produced in the stomach and plays an essential role in digestion. Gastric acid, which is primarily composed of hydrochloric acid, helps to break down food in the stomach and facilitate the absorption of nutrients. It also plays a role in protecting the body against harmful bacteria and other pathogens that may be present in food. However, excessive production or secretion of gastric acid can lead to a range of medical conditions, including gastroesophageal reflux disease, GERD, and peptic ulcers. These conditions can cause discomfort and pain, and can have serious long-term health implications if not treated properly. Similarly, sulfuric acid and nitric acid can also have important biological effects. For example, nitric oxide, NO, which is produced by the reaction of nitric acid with various substances in the body, is a key signaling molecule that plays a role in regulating blood pressure and other physiological processes. Sulfuric acid can also have significant environmental and health implications. When released into the environment, sulfuric acid can contribute to acid rain, which can have a range of negative effects on ecosystems and human health. In addition, exposure to sulfuric acid can cause respiratory problems, skin irritation, and other health issues. Inorganic acids also play a significant role in the field of analytical chemistry. For example, sulfuric acid and nitric acid are commonly used in the preparation of samples for elemental analysis by techniques such as atomic absorption spectroscopy and inductively coupled plasma mass spectrometry. In these techniques, the sample is treated with an acid solution to break down the matrix and release the elements of interest for analysis. The acid solution also helps to dissolve any organic or inorganic impurities that may interfere with the analysis. In addition, inorganic acids such as hydrochloric acid are used in the calibration of pH meters and other analytical instruments. These instruments rely on accurate measurements of pH to provide information about the chemical properties of a solution. And the use of standardized acid solutions is essential for ensuring accurate and reproducible results. Furthermore, inorganic acids are also used in the development of new analytical techniques and methods. For example, researchers have developed novel approaches for the detection and quantification of biological molecules such as proteins and nucleic acids using acid-catalyzed reactions. Overall, the use of inorganic acids in analytical chemistry is essential for a wide range of applications, from environmental monitoring to medical diagnostics. Ongoing research and development in this field are likely to continue to drive innovation, leading to new and more efficient ways of using these acids in analytical applications. In addition to their analytical applications, inorganic acids also have important implications for materials science and engineering. For example, sulfuric acid is commonly used in the production of lead-acid batteries, which are widely used in automotive and other applications. Sulfuric acid is also used in the production of a wide range of other materials, including fertilizers, detergents, and pigments. In addition, it is used in the processing of ores and metals, such as copper and zinc, to create a range of products, including wires, pipes, and tubes. Similarly, nitric acid is used in the production of a range of materials, including fertilizers, dyes, and explosives. It is also used in the manufacturing of semiconductors and other electronic components, which are essential for a wide range of modern technologies. Hydrochloric acid is also used in the production of a range of materials, including pharmaceuticals, plastics, and rubber. It is also used in the pickling of metals and in the cleaning and maintenance of swimming pools and other facilities. Inorganic acids also have important implications for the field of geology and earth sciences. For example, sulfuric acid plays a significant role in the formation of acid sulfate soils, which are soils that have been impacted by acidification due to the oxidation of sulfide minerals. Acid sulfate soils can have significant environmental and agricultural implications, including reduced crop yields and increased risk of soil erosion. Understanding the processes involved in the formation of acid sulfate soils is essential for developing effective strategies for managing and mitigating these impacts. Similarly, inorganic acids such as hydrochloric acid and nitric acid can also play a role in the weathering and erosion of rocks and minerals. Acidic solutions can react with minerals in the rock, leading to the dissolution and alteration of the mineral structure. These processes can have significant implications for the formation of geological formations and the overall evolution of the Earth's crust. Understanding the mechanisms of rock weathering and mineral dissolution is essential for developing a comprehensive understanding of the Earth's geology and geological history. Chemical reactions and manufacturing processes in the industry that manufacture and use polymeric materials such as polycarbonate and polyvinyl chloride, PVC. Chemical reactions and production processes are essential components of the polymer industry, which produces a wide range of materials for use in a variety of applications. Two important types of polymers are polycarbonate and polyvinyl chloride, PVC, which have unique properties that make them suitable for a range of applications. Polycarbonate is a thermoplastic polymer that is known for its exceptional strength, toughness, and optical clarity. It is commonly used in the production of a range of products, including eyeglasses, automotive components, and electronic components. One important reaction involved in the production of polycarbonate is the reaction between bisphenol A and phosgene. In this reaction, bisphenol A is reacted with phosgene to produce polycarbonate and hydrochloric acid. This reaction is typically carried out in a solvent, such as methylene chloride, and requires careful control of temperature and pressure to ensure the formation of high-quality polycarbonate. The resulting polycarbonate can then be processed into various forms, such as sheets, films, and molded parts, for use in a variety of applications. Polyvinyl chloride, PVC, is another important polymer that is widely used in the production of a range of products, including pipes, window frames, and flooring. PVC is a thermoplastic material that is known for its excellent durability, chemical resistance, and low cost. One important reaction involved in the production of PVC is the polymerization of vinyl chloride monomer. In this reaction, vinyl chloride monomer is polymerized to form PVC, which can then be processed into various forms for use in a range of applications. The polymerization of vinyl chloride can be carried out using a range of techniques, including suspension polymerization, emulsion polymerization, and bulk polymerization. Each of these techniques has its own advantages and disadvantages, depending on the specific application and desired properties of the final product. In addition to the production of polycarbonate and PVC, the polymer industry also involves a range of other reactions and production processes. For example, the production of other thermoplastics, such as polyethylene and polypropylene, involves the polymerization of ethylene and propylene monomers, respectively. Similarly, the production of thermosetting polymers, such as epoxy resins and phenolic resins, involves the cross-linking of polymer chains through the use of curing agents and other additives. The production of polymers also involves a range of processing techniques, including extrusion, injection molding, and blow molding. These techniques are used to shape the polymer into the desired form and impart specific properties, such as strength, flexibility, and chemical resistance. In addition to the production of polycarbonate and PVC, the polymer industry also involves the use of a wide range of additives and modifiers to enhance the properties of polymer materials. These additives and modifiers can impart specific properties, such as flame retardancy, UV resistance, and impact resistance, and can also improve processing and handling characteristics. One important class of additives used in the polymer industry is plasticizers, which are used to increase the flexibility and workability of polymer materials. Plasticizers are typically low molecular weight compounds that are added to the polymer matrix to improve its flexibility and reduce its stiffness. Another important class of additives used in the polymer industry is flame retardants, which are used to reduce the flammability of polymer materials. Flame retardants can be added to the polymer matrix or applied as a coating to the surface of the material, and can help to reduce the risk of fire and improve the safety of polymer-based products. Other important additives used in the polymer industry include stabilizers, antioxidants, and UV absorbers, which are used to improve the durability and longevity of polymer materials. These additives can help to prevent degradation and discoloration of the polymer over time, and can also improve its resistance to environmental factors such as heat, light, and moisture. The use of additives and modifiers in the polymer industry is essential for the development of new and improved polymer materials that meet the specific needs of various applications. Ongoing research and development in this field are likely to continue to drive innovation and lead to the development of new and more effective additives and modifiers. Furthermore, the polymer industry also has important implications for sustainability and environmental protection. The production and use of polymer materials can have significant environmental impacts, including the generation of waste and the release of greenhouse gases and other pollutants. To address these issues, the polymer industry is increasingly focused on the development of sustainable and environmentally friendly materials and production processes. This includes the use of renewable and biodegradable materials, as well as the development of closed-loop recycling systems that minimize waste and reduce the environmental impact of polymer production and use. Another important aspect of the polymer industry is the development of new and innovative processing techniques that enable the production of complex and highly functional polymer materials. One such technique is additive manufacturing, also known as 3D printing, which allows for the production of highly complex and precise polymer structures using computer-controlled layer-by-layer deposition. Additive manufacturing has the potential to revolutionize the polymer industry, enabling the production of highly customized and complex parts with minimal waste and reduced lead times. This technology is already being used in a range of applications, such as aerospace, healthcare, and consumer products, and is likely to continue to drive innovation and new product development in the polymer industry. Another important development in the polymer industry is the use of biopolymers, which are derived from renewable and biodegradable sources such as corn starch, cellulose, and chitin. Biopolymers offer a range of advantages over traditional fossil fuel-based polymers, including reduced environmental impact, improved biodegradability, and reduced dependence on non-renewable resources. Biopolymers are already being used in a range of applications, such as packaging, textiles, and biomedical devices. And ongoing research and development in this field are likely to continue to drive innovation and lead to the development of new and more advanced biopolymer materials. Furthermore, the polymer industry is also increasingly focused on the development of materials with improved sustainability and circularity. This involves the development of materials that can be easily recycled or biodegraded at the end of their useful life, as well as the development of closed-loop recycling systems that minimize waste and enable the recovery of valuable materials from end-of-life products. The polymer industry also has important implications for the field of nanotechnology, which involves the manipulation and control of materials at the nanoscale. Polymer-based nanocomposites are a rapidly growing field, with potential applications in a wide range of industries, including electronics, healthcare, and energy. Nanocomposites are materials that incorporate nanoparticles into a polymer matrix, resulting in materials with unique and enhanced properties. For example, the addition of carbon nanotubes to a polymer matrix can result in materials with improved mechanical strength, electrical conductivity, and thermal stability. Similarly, the addition of nanoparticles to a polymer matrix can result in materials with enhanced optical properties, such as increased transparency or coloration. The development of polymer-based nanocomposites is an active area of research and development, with ongoing efforts to optimize the properties of these materials for various applications. Another important development in the polymer industry is the use of smart materials, which are materials that can change their properties in response to external stimuli, such as temperature, light, or electrical fields. Smart materials have a range of potential applications, including in sensors, actuators, and drug delivery systems. Polymer-based smart materials can be designed to respond to a wide range of stimuli. And ongoing research in this field is focused on developing new and more advanced materials with improved functionality and performance. Applications of organic compounds in the production and use of chemical products used in the seafood and aquatic product industry. Chemical reactions and production processes in the industrial manufacturing. And use of polymers like polycarbonate and polyvinyl chloride, PVC introduction. Polymers are essential materials in our daily lives. They are used in various applications, such as packaging, construction, textiles, automotive, and electronics. Polymers are made up of long chains of repeating units called monomers. The properties of polymers depend on the type and structure of the monomers used to make them. In this article, we will focus on two types of polymers, polycarbonate and polyvinyl chloride, PVC. We will discuss the chemical reactions involved in their production and the industrial manufacturing and use of these polymers. Polycarbonate. Polycarbonate is a strong, transparent, and lightweight polymer used in a variety of applications, such as eyeglass lenses, CD/DVDs, electronic components, and automotive parts. The monomer used to make polycarbonate is bisphenol A, Pa, and phosgene. The reaction between Pa and phosgene is a condensation polymerization reaction. During this reaction, Pa and phosgene react to form a polycarbonate chain, and hydrochloric acid is produced as a byproduct. The reaction can be represented as follows: Pa plus phosgene polycarbonate plus HCl. The reaction is carried out in a solvent, such as methylene chloride or chloroform, to dissolve the reactants and prevent the formation of unwanted byproducts. The reaction is also carried out at high temperatures and pressures to increase the rate of reaction and yield a high molecular weight polymer. The resulting polycarbonate is then purified, dried, and processed into various products. Polyvinyl chloride, PVC polyvinyl chloride, PVC, is a versatile polymer used in various applications, such as pipes, flooring, window frames, and electrical cables. The monomer used to make PVC is vinyl chloride, VC. The reaction between VC and a catalyst is a free radical polymerization reaction. During this reaction, VC is converted into a PVC chain, and hydrogen chloride is produced as a byproduct. The reaction can be represented as follows: VC plus catalyst PVC plus HCl. The catalyst used in the reaction is usually a peroxide or an azo compound. The reaction is carried out at high temperatures and pressures to increase the rate of reaction and yield a high molecular weight polymer. The resulting PVC is then purified, dried, and processed into various products. Industrial manufacturing and use. The industrial manufacturing of polycarbonate and PVC involves several steps, such as raw material preparation, polymerization, purification, drying, and processing. The raw materials used in the production of polycarbonate and PVC are usually obtained from petrochemical sources. In the case of polycarbonate, BA and phosgene are mixed in a reactor vessel, along with a solvent and a catalyst. The mixture is then heated to a high temperature and pressure, and the reaction is allowed to proceed for several hours. The resulting polycarbonate is then purified and dried, and it is processed into various products, such as sheets, films, and molded parts. In the case of PVC, VC is polymerized in a reactor vessel, along with a catalyst and a solvent. The reaction is carried out at a high temperature and pressure, and the resulting PVC is then purified and dried. The purified PVC is then processed into various products, such as pipes, fittings, and profiles, using extrusion or injection molding techniques. The use of polycarbonate and PVC in various applications has its advantages and disadvantages. Polycarbonate is a strong and durable material that is resistant to impact and UV radiation. However, it is also prone to scratching and yellowing over time. PVC is a versatile material that is easy to process and has excellent chemical resistance. However, it is also a controversial material due to its environmental impact and potential health hazards associated with its production and use. Conclusion: Polycarbonate and PVC are two important polymers used in various applications. The production of these polymers involves different chemical reactions and industrial manufacturing processes. The use of these polymers has its advantages and disadvantages, and their environmental impact and health hazards should be carefully considered. As the demand for polymers continues to grow, it is important to explore new and sustainable ways to produce and use these materials. Polymers are a crucial component of modern society, and their production and usage continue to expand. In this article, we will explore the chemical reactions and industrial processes involved in the production and use of two important polymers, polycarbonate and polyvinyl chloride, PVC. Polycarbonate is a transparent, lightweight, and durable polymer used in a range of applications such as eyeglass lenses, DVDs, and automotive parts. The primary monomer used to produce polycarbonate is bisphenol A, BA, and phosgene. The reaction between these compounds is a condensation polymerization reaction that produces a polycarbonate chain and hydrochloric acid. The production process begins by mixing PA and phosgene in a reactor vessel, along with a solvent and a catalyst. The mixture is heated to high temperatures and pressure, and the reaction is allowed to continue for several hours. The resulting polycarbonate is then purified, dried, and processed into various products. Polyvinyl chloride, PVC, is a versatile polymer used in a wide variety of applications such as pipes, window frames, and electrical cables. The primary monomer used to produce PVC is vinyl chloride, VC. The reaction between VC and a catalyst is a free radical polymerization reaction that produces a PVC chain and hydrogen chloride. The production process for PVC begins by polymerizing VC in a reactor vessel, along with a catalyst and a solvent. The reaction is carried out at high temperatures and pressure, and the resulting PVC is then purified, dried, and processed into various products. The industrial manufacturing of polycarbonate and PVC involves several steps, such as raw material preparation, polymerization, purification, drying, and processing. The raw materials used in the production of polycarbonate and PVC are typically derived from petrochemical sources. Both polycarbonate and PVC have their advantages and disadvantages. Polycarbonate is a strong and durable material that is resistant to impact and UV radiation, but it is also prone to scratching and yellowing over time. PVC is a versatile material that is easy to process and has excellent chemical resistance, but it has environmental concerns and potential health hazards associated with its production and use. In conclusion, the production and use of polycarbonate and PVC involve complex chemical reactions and industrial processes. As these materials continue to be in demand, it is crucial to explore new and sustainable methods of their production and use. At the same time, it is important to consider their environmental impact and potential health hazards associated with their production and use. By doing so, we can ensure the safe and sustainable use of these important polymers in modern society. Polycarbonate and PVC are two of the most widely used polymers in various industrial and commercial applications. While they share some similarities in their production processes, they have distinct chemical and physical properties that make them suitable for different uses. Polycarbonate is a thermoplastic polymer that is known for its high impact resistance, transparency, and thermal stability. Applications of organic compounds in the production and use of chemical products used in the seafood and aquatic product industry. Chemical reactions and production processes play a critical role in the manufacturing and use of polymers in various industries. Polymers are large molecules composed of repeating units known as monomers, and they have a wide range of applications in industries such as packaging, automotive, construction, and electronics. One important class of polymers used in industry is polycarbonate, which is a thermoplastic polymer that is known for its high strength, transparency, and impact resistance. Polycarbonate is produced through the reaction of bisphenol A and phosgene, which results in the formation of a polymer chain. The production process for polycarbonate involves several steps, including the synthesis of bisphenol A and the reaction between bisphenol A and phosgene. After the polymerization reaction, the resulting polycarbonate is purified and processed into various forms, such as sheets, films, and pellets, which can be used in a wide range of applications. Another important class of polymers used in industry is polyethylene terephthalate (PET), which is a thermoplastic polymer that is used in a variety of applications, including packaging, textiles, and electronics. PET is produced through the reaction of terephthalic acid and ethylene glycol, which results in the formation of a polymer chain. The production process for PET involves several steps, including the synthesis of terephthalic acid and ethylene glycol. The reaction between terephthalic acid and ethylene glycol, and the polymerization reaction. After the polymerization reaction, the resulting PET is purified and processed into various forms, such as fibers, films, and bottles, which can be used in a wide range of applications. In addition to the production processes, chemical reactions also play a critical role in the modification and functionalization of polymers for various applications. For example, the addition of various monomers and additives can impart specific properties to polymers, such as flame retardancy, UV resistance, and impact resistance. One important modification process is grafting, which involves the attachment of one or more monomers onto a polymer chain. Grafting can be used to introduce new functional groups onto the polymer chain, improving its compatibility with other materials or modifying its physical properties. Another important modification process is cross-linking, which involves the formation of covalent bonds between polymer chains. Cross-linking can be used to improve the mechanical properties of polymers, such as stiffness and strength, or to impart specific properties, such as thermal stability, chemical resistance, and electrical conductivity. Overall, the production and modification of polymers involve a wide range of chemical reactions and production processes that are critical for the development of new and improved polymer materials for various applications. Ongoing research and development in this field are likely to continue to drive innovation and lead to the development of new and more advanced polymers with improved properties and performance. In addition to the production and modification of polymers, the recycling and sustainability of polymers have become increasingly important issues in the industry. The use of petroleum-based polymers has led to significant environmental concerns, including the accumulation of plastic waste in landfills and oceans. One important approach to addressing these concerns is the development and use of biodegradable polymers, which can be broken down by natural processes, such as microbial degradation, into non-toxic substances. Biodegradable polymers can be derived from renewable sources, such as starches and cellulose, or from synthetic sources, such as polylactic acid, PLA, and polyhydroxyalkanoates, PHA. The recycling of polymers is another critical aspect of sustainability in the industry. Recycling allows for the recovery and reuse of valuable materials, reducing waste and the need for new material production. One common approach to polymer recycling is mechanical recycling, which involves the shredding and melting of polymer waste into new products. Another approach to polymer recycling is chemical recycling, which involves the breakdown of polymers into their constituent monomers or other building blocks, which can then be used to produce new polymers or other chemicals. Chemical recycling has the potential to recover a wider range of polymers, including those that are difficult to recycle using mechanical recycling. Furthermore, the development of circular economy models in the polymer industry has become increasingly important. This involves designing products and production processes that minimize waste and prioritize the recovery and reuse of materials. One example of this is the use of closed-loop recycling systems, which allow for the recovery and reuse of materials from end-of-life products, reducing the need for new material production. In addition to these sustainability efforts, the polymer industry is also focused on the development of advanced materials. and technologies that can address important societal and environmental challenges. For example, polymer-based materials are being developed for use in water purification and desalination, as well as for the removal of pollutants from air and water. Similarly, polymer-based materials are being developed for use in energy storage and conversion, such as in batteries, fuel cells, and solar cells, with the potential to improve the efficiency and performance of these technologies. Overall, the polymer industry is a dynamic and innovative field that is essential for a wide range of applications and industries. Ongoing research and development in this field are likely to continue to drive innovation and lead to the development of new and more advanced polymer materials, production processes, and sustainable technologies that meet the complex needs of society while also addressing important environmental and societal challenges. One area of research and development in the polymer industry is the use of smart and responsive polymers, which can change their properties in response to external stimuli, such as temperature, pH, or light. These polymers have a range of potential applications, including in drug delivery, tissue engineering, and sensors. Smart polymers can be designed to respond to specific stimuli, allowing for precise control over their properties and behavior. For example, temperature-responsive polymers can undergo a reversible phase transition from a hydrophilic to a hydrophobic state in response to changes in temperature, making them useful for drug delivery applications. Similarly, pH-responsive polymers can undergo changes in their ionization state in response to changes in pH, allowing for targeted drug delivery to specific tissues or cells. In addition to their use in drug delivery and tissue engineering, smart polymers are also being developed for use in sensors and actuators. For example, light-responsive polymers can undergo changes in their shape or chemical composition in response to light, allowing for the development of light-driven actuators and sensors. Another important area of research in the polymer industry is the development of biocompatible and biodegradable polymers for use in medical applications. These polymers are designed to be compatible with biological systems and can be broken down by natural processes, reducing the risk of toxicity or other adverse effects. Biodegradable polymers are being developed for use in drug delivery, tissue engineering, and medical devices, such as sutures and implants. For example, synthetic polymers, such as PLA and FA, are being used to develop biodegradable implants for bone repair and regeneration. Biocompatible polymers are also being developed for use in tissue engineering and other medical applications. These polymers are designed to mimic the properties of biological tissues and can be used to support the growth and regeneration of various types of tissues, such as skin, cartilage, and bone. Applications of organic compounds in the production and use of rubber products, including synthetic and natural rubber types. Organic compounds are widely used in the production and use of rubber products in various industries. Rubber is a polymer material that is known for its elasticity, toughness, and resistance to abrasion. And it has a wide range of applications in industries such as automotive, construction, and consumer goods. Rubber can be broadly classified into two categories: synthetic rubber and natural rubber. Synthetic rubber is produced from various organic compounds, while natural rubber is derived from the latex of rubber trees. One important class of organic compounds used in the production of synthetic rubber is styrene butadiene rubber, SBR, which is a copolymer of styrene and butadiene. SBR is widely used in the production of tires, as well as various other rubber products, such as conveyor belts and shoe soles. Another important class of organic compounds used in the production of synthetic rubber is polybutadiene rubber, PBR, which is a polymer of butadiene. PBR is known for its high elasticity and is used in the production of various rubber products, including tires, hoses, and belts. In addition to SBR and PBR, other organic compounds, such as neoprene, nitrile rubber, and EPDM, are also widely used in the production of synthetic rubber for various applications. Natural rubber, on the other hand, is derived from the latex of rubber trees and is an important material for various industries, including automotive, construction, and consumer goods. Natural rubber is known for its high elasticity, low hysteresis, and excellent tear and abrasion resistance. Organic compounds, such as accelerators and vulcanizing agents, are used in the production of natural rubber to improve its properties and performance. For example, sulfur is commonly used as a vulcanizing agent to cross-link the polymer chains in natural rubber, resulting in improved strength, elasticity, and durability. Rubber products are used in various applications in industries such as automotive, construction, and consumer goods. In the automotive industry, rubber products are used in tires, belts, hoses, and other components, where their durability, resistance to abrasion, and elasticity are critical. In the construction industry, rubber products are used in roofing, flooring, and insulation, where their resistance to weathering, moisture, and chemicals are important properties. In the consumer goods industry, rubber products are used in various applications, such as footwear, toys, and medical devices, where their elasticity, durability, and biocompatibility are important factors. In addition to traditional rubber products, organic compounds are also used in the production of advanced rubber materials with unique properties and functionalities. For example, liquid silicone rubber, LSR, is a silicone-based rubber material that is used in various applications, such as medical devices and electronics. LSR is known for its biocompatibility, heat resistance, and electrical insulation properties, making it useful in various medical and electronic applications. LSR is also commonly used in the automotive industry for sealing and gasket applications, where its resistance to high temperatures and chemicals are important properties. Another advanced rubber material that is widely used in various industries is fluorinated rubber, FKM, which is known for its excellent resistance to chemicals, heat, and oil. FKM is commonly used in the automotive industry for fuel system components, as well as in various other applications, such as aerospace, oil and gas, and chemical processing. Organic compounds are also used in the development of functional rubber materials, such as conductive rubber and self-healing rubber. Conductive rubber is a rubber material that can conduct electricity, making it useful in various electronic applications, such as touchscreens and sensors. Self-healing rubber, on the other hand, is a rubber material that can repair itself when damaged, reducing the need for frequent replacements and repairs. Self-healing rubber has potential applications in various industries, such as automotive, construction, and aerospace, where its durability and resistance to damage are important properties. Furthermore, the use of sustainable and eco-friendly materials and production processes in the rubber industry is becoming increasingly important. The development of bio-based rubber materials, such as natural rubber derived from sustainable sources, is one approach to reducing the environmental impact of rubber production. Another important area of research and development in the rubber industry is the use of nanotechnology to design and develop advanced rubber materials with unique properties and functionalities. Nanotechnology involves the manipulation and control of materials at the nanoscale, which allows for the creation of materials with novel properties and behaviors. In the rubber industry, nanotechnology is being used to develop advanced rubber materials, such as nanocomposites and nanofibers, which have unique strength, thermal, and electrical properties. Nanocomposites are materials that contain nanoparticles dispersed throughout a rubber matrix, resulting in improved mechanical and thermal properties. These materials have potential applications in various industries, including automotive, aerospace, and consumer goods. Nanofibers, on the other hand, are ultrafine fibers with diameters in the nanometer range. These fibers have unique properties, such as high surface area to volume ratio, high porosity, and high strength, which make them useful in various applications, such as filtration, tissue engineering, and energy storage. In addition to the use of nanotechnology, the rubber industry is also focused on the development of sustainable and eco-friendly materials and production processes. One approach to reducing the environmental impact of rubber production is the development and use of bio-based rubber materials, such as natural rubber derived from sustainable sources. In addition, the use of sustainable production processes, such as closed-loop recycling systems and the use of renewable energy sources, is also a critical aspect of sustainability in the industry. Another important area of research in the rubber industry is the development of rubber materials with advanced functionalities, such as self-cleaning and anti-fouling properties. These materials have potential applications in various industries, such as marine, healthcare, and food processing, where their ability to repel dirt, bacteria, and other contaminants is important. Rubber recycling is another important aspect of sustainability in the rubber industry. The recycling of rubber products, such as tires, can help reduce waste and conserve resources. One approach to rubber recycling is mechanical recycling, where rubber products are shredded, ground, and processed into new rubber products. This approach is commonly used for the recycling of tires, where the shredded rubber is used to produce new tires, as well as various other rubber products, such as playground surfaces and athletic tracks. Another approach to rubber recycling is chemical recycling, where rubber products are broken down into their constituent compounds and used to produce new materials. This approach is still in the early stages of development, but it has the potential to produce high-quality recycled rubber materials with properties similar to those of virgin rubber. In addition to recycling, the rubber industry is also focused on reducing the environmental impact of rubber production and use through the development of sustainable and eco-friendly materials and production processes. One approach to reducing the environmental impact of rubber production is the use of renewable energy sources, such as solar and wind power, to power rubber manufacturing facilities. The use of renewable energy sources can help reduce greenhouse gas emissions and conserve resources. Furthermore, the development of sustainable materials, such as bio-based rubber materials and recycled rubber, can help reduce the reliance on petroleum-based materials and conserve resources. The rubber industry is also focused on addressing important societal challenges, such as improving worker safety and promoting social responsibility. The production of rubber products involves various processes that can pose risks to worker health and safety, such as exposure to chemicals and machinery hazards. To address these challenges, the rubber industry has implemented various initiatives and programs to promote worker safety and health.